Okay, thanks. I'm going to start by thanking the organizers for organizing this workshop and inviting us to give these talks. So I'm going to give the first in 4 talks, in a series of 4 talks on this topic, which has received a lot of attention in the last decade or so. So let's just start. So we all know what the classical coding problem is, but let me remind you what it is. So suppose you have 2 parties who want to communicate. One of the parties has this input x, which is an n-bit string, and wants to send that string over to a second party. But he can't just send the string in the clear because some of the transmissions will have errors. Okay. How do we solve this problem? It's a problem that we've studied for a long time, and today we know a lot about how to solve it. We know that you can take the string and encode it into an error correcting using an error correcting code. So you take the short string that's n bits long and encode it into potentially a longer string using this encoding function in such a way that if you transmit now this code word, then even if there are errors, the receiving party can somehow decode what the intended transmission was. Okay. So there's a way to encode the n-bit string and a way to decode after there are errors. And today we know how to solve this kind of problem with these kinds of parameters. We can encode any n-bit string using order n bits in such a way that as long as at most 25% of the transmission is corrupted, you can recover the original transmission. So I want to say there are multiple ways to think about how the errors happen. You can imagine that the errors happen randomly. That was how this thing was studied initially. But it also makes sense to consider what happens when the errors are really adversarial. So you just know that some 25% of the bits that are transmitted are corrupted, and you don't know anything else about how they're distributed. So that's kind of what was studied classically in coding theory. The setup that this tutorial is about is when the communication is interactive, when it's not just one way. Okay. So now we have an interactive protocol that's being run between 2 parties. The first party knows an input x, the second party knows some input y, and they have a conversation based on these inputs. So the first party sends a message m1 that depends only on x. Then the second party responds with a message that depends both on y and the messages in the past, and so on. Okay, so in every step, one of the parties sends a message that depends on his input and all the messages that have been transmitted so far. So the question that we want to ask is, what's the best way to deal with errors in this situation? So how can we deal with errors when we want to carry out this long conversation?
You didn't say what the goal is. Does he have to know x and he has to know y? Or?
We don't know what the goal is. We just like to simulate the behavior of this protocol. So imagine that this protocol was designed under the assumption that there would be no errors, and the protocol achieves some functionality. We just like to be able to achieve the same functionality. Just simulate the messages in this protocol in the situation when there are errors. So, obviously this is a generalization of what we just talked about in the last slide, because that, if there's just one message, that's the case that corresponds to the last slide. If you're just sending x across, that's a special case of such an interactive protocol. Okay, so it's a beautiful question. It was first studied by Shulman in the early 90s, who also gave a really beautiful solution to this problem. But let me first say why at least I care about interactive communication. And the reason is as a complexity theorist, interactive communication shows up anytime you want to measure complexity in many situations. It's hard to imagine any computational model where you cannot abstractly find 2 parties that are communicating with each other interactively. So for example, here's a Boolean circuit. It's something that sits in your cell phone and all of our computers. So you can always take such a circuit and divide up the gates into two parts, like the left side and the right side. And now if you think of what happens when you execute the circuit, you see that what's going on is these sides are interacting with each other. They're exchanging messages with each other as they compute. Okay. So hiding in this circuit is an interactive protocol between sort of the left brain of the circuit and the right brain of the circuit. So a different way to phrase the question that I just asked is, suppose you have two circuits that are connected with n wires. Is there some way to encode them to get new circuits that now have order n wires going between them, say a small number of wires going between them, in such a way that this new circuit achieves the same functionality as this old circuit, even if a large fraction of the wires between these two parts fail? Is there some way to do that? And it turns out that there is. That's what we're going to see. Okay, so that's the question we're after. Is there some way to take this protocol and encode it in such a way that it still works? It still simulates the original protocol, even if there's many errors in the transmissions. Are there any questions about the model, the setup? All right. So given what we know about coding, using error correcting codes to encode single messages, the first thing maybe that you would think about here is maybe we can just use those ideas to solve the problem in this setting also, right? Maybe we can just use codes to protect every message in the protocol. And that does work, but it doesn't work that well, okay? So you could do that. You could try and use an error correcting code to protect every message of the protocol. But the problem is, because the protocol is interactive, an adversary just needs to ruin a single message in the entire protocol to ruin the entire conversation, right? So an adversary could just concentrate all their errors onto a single message. So imagine, for example, in the worst case, that the protocol just has messages that are 1 bit long. Okay, so they're just 1 bit long messages and many such messages. Then no matter what error correcting code you could use, the adversary could just concentrate their errors onto one of those messages, which would just be 1 over n fraction of the entire communication, and ruin the whole conversation. Okay. So this is not such a good idea. And what we're going to see are many ideas, or some ideas to solve this problem in a way that's better than doing this. Okay, so here's, before I go on, let me just give you a broad plan for what the talks in the tutorial are going to be about. So today, what I'll talk about is a basic solution to this problem. The solution that I'll talk about is work of Braverman and myself, which builds on the initial ideas of Schulman. And then I want to show you two interesting applications of the solution. The first is to recovering from errors in circuits in a way that's a little different from what I showed you in a few slides ago. The next is an application that's kind of surprising to metric embeddings. Okay. And finally, time permitting, I'll end with a candidate explicit solution, a candidate efficient solution to this problem. On Tuesday, Bernard will talk about some computationally efficient solutions to this problem. He'll discuss topics like list decoding in this setting. On Wednesday, Ranraz and Bernard will talk about interactive channel capacity. How do you figure out exactly what the right capacity is for a channel in this setting? And in the last talk, on Thursday, Klim and Rangeles will talk about list decoding and multi-party communication in the setting. How do you handle more than 2 parties So that's a broad outline. And now let's return to the problem at hand. So I want to start by telling you how you can, what's a basic way to solve this problem. So it's hard to think about what every possible communication protocol can look like. So instead, what I'm going to do is I'm going to tell you sort of a complete problem for communication protocols, and we'll figure out how to solve that problem in the presence of errors. It'll turn out that once you know how to solve this problem in the presence of errors, you can encode any protocol so that it succeeds even in the presence of errors. Okay? So what's the complete problem? It's the pointer jumping problem. So here, the inputs correspond to edges in a complete binary tree. So there's sort of this underlying complete binary tree. It has depth n. And each party knows some subset of the edges of this tree. Okay? So every edge at even depth in this tree, every vertex in this tree has exactly one edge coming out of it to a child. Okay, so that's the promise of the problem. And every such edge that comes out of an even depth vertex is known to the first party. And the second party knows all the edges that come out of vertices of odd depth. Okay? So all of the blue edges here are the edges that come out of even depth vertices, and they're known to the first party. And the second party knows all of the edges that come out of the odd depth vertices. And their goal is to find the unique red-blue sort of the unique path in this tree that's in both parties' edges. Okay, which in this case you see is this one. So it's the path that goes from the root to this vertex and then to this vertex, and so on. Okay, so there's a trivial n-bit communication protocol for this problem, which is that the first party can send a bit to say indicate what the first edge is, the edge that he knows that comes out of the root. Then the second party can respond with a bit that says what the second edge is of the path, and so on, right? So in this way, after n bits of communication, they'll have figured out what the path is that goes from the root to a leaf in this tree. All right. So the reason that this problem, so first let me say, so what we're going to spend most of the talk on is trying to understand how can we solve this problem when some of the transmissions of the parties are corrupted. Okay. That's what we like to do. We're given the parties know these edges, and they're given this input, and they would like to solve this problem efficiently, but some of the symbols, some of their transmissions may be corrupted adversarially. So the reason that this problem is sort of complete for communication protocols is, given any communication protocol, you can think of each of these vertices as representing a partial transcript of the messages of the players, and this edge is representing what the next player would say. Okay, so kind of this input captures the behavior of the protocol in all possible inputs and all possible situations. And given that behavior, the first party knows how he will behave on these nodes, and the second party knows how he would behave when the protocol is in these states. So given that description, we'd like to figure out what the outcome of the protocol will be. Okay, so this kind of captures pretty much what any protocol does. Okay, but we'll just now focus on this problem.
Just make it a bit, I understand the idea very well.
Yeah.
Can you make an explicit statement? In what sense this is complete?
It's complete in the sense that if you have, there's parameters, but ignoring parameters, if you solve this problem, if you can figure out how to solve this problem with, say, communication order n and some error rate, then that means that you can take any protocol whose communication is n and simulate it by another protocol with communication order n, even in the presence of some fraction of errors.
Maybe it's easier to say that for any communication protocol that runs in n rounds, there exist an instance of input for pointer jumping problem of depth 2n, which solves this problem.
Exactly. Yeah. Good. Yeah. So for any communication protocol, there's a way to reduce it to this problem with a factor of 2. Okay. So that's why it's enough to just think about this problem. So here's the plan for how I'm going to show you how to solve this problem. So it'll turn out to be much easier to think about solving this problem not using a protocol that has bits as its transmissions, but symbols from a very large alphabet. So that's what I'll do first. I'll first show you how to solve this problem if I'm allowed to send you symbols from a very large alphabet. And then I'll explain why the same solution essentially works with a smaller alphabet. The same solution also gives you a solution with just bits as your transmission. Okay. So to use a large alphabet, so for now we're just going to imagine that we're allowed to send symbols from a huge alphabet. So given that, I'm going to first explain just the original protocol, the trivial protocol that we talked about that exchanges n bits. But I'm going to explain how to run it using a huge alphabet. Okay, I'm going to make it a little worse. And this will be helpful when we try and make the protocol resilient to errors. So here's a different way to view exactly the same protocol. So every alphabet symbol is now going to represent a distinct edge in this picture. Okay, a distinct edge of this tree. So that's a huge alphabet, size something like 2 to the n. And one way to view that protocol is you can view it like this. In every step, a party announces an edge. And the edge they announce is the unique edge that kind of extends the path that's given in the set of edges that have been announced so far. So in the first step, the first party announces this edge. Okay. Then the second party announces this edge. And now, A union B form this path. And the first party knows how to extend that path, so the first party announces this edge. And so on, right? So in every step, someone who can extend the path that they know about so far announces the edge that helps to extend it, and eventually they find the leaf that they're interested in. Okay, so that's the trivial protocol. Now, what happens when there are errors? The problem is that from the first party's perspective, he's not entirely sure what edges were announced by the second party, right? Because some of the messages he gets are corrupted. So for example, it might be that the first party announces this edge, and then the second party announces this edge, but the first party receives this edge because there's an error.
So now the adversary not only chooses which symbols to corrupt, but he gets to choose what they are corrupted to?
Yeah, the adversary is all powerful. He knows everything the players know, and he corrupts in an arbitrary way. So, the adversary would not say that the second party announced, something far away, because then the first party would know that that's an error, right? The adversary will say something like this. This is what the second party said.
So in that case, I don't understand how this is different from binary case.
It's not different yet, but my solution is going to be a large alphabet solution, my first solution. Right? And now I'm explaining why it's failing. So I've just made things worse with a large alphabet because keeping in mind that my solution will later exploit the large alphabet. So the reason it doesn't work is exactly this, right? The first party doesn't know what's going on. So now the first party might announce this edge, but the adversary can come in again and corrupt that transmission and make the second party think that the first party actually announced this edge. So in this way, the adversary can kind of derail this conversation to make the parties sort of just exchange useless information. So that's kind of why just the trivial protocol does not work as is. So we're going to try and patch up this protocol to make it work. And the way we're going to do that is we're going to use a beautiful combinatorial object that was invented by Schulman for this purpose called a tree code. So let me explain what it is, and then we'll see some of its nice properties, and then finally use it to solve that problem. So what is a tree code? It's a D-ary tree code is a D-ary tree where all the edges of the tree are labeled by symbols from some alphabet. So all the edges of the tree are labeled by symbols from an alphabet. And the property we want of this labeling is the following distance property. If you take any two vertices u and v in the tree, which are at the same depth, and look at the path that goes from u to the least common ancestor of u and v to the least common ancestor of u and v, then this path has a large Hamming distance on it. Okay. So take any two vertices u and v which are at the same depth, and look at their common ancestor here. And then if you look at the labels from that ancestor to u and that ancestor to v, and then just write down these labels as a string, the Hamming distance between these two strings must be large. Okay? So the distance of the code is 1 minus epsilon if the relative distance between these two strings for every such u and v is at least 1 minus epsilon. Okay? It means the Hamming distance between a and b is at least 1 minus epsilon times the length of a and b. Okay, so that's what a tree code is. It's a labeling of the tree that has this property. Now, one way to achieve this is to just label every edge in the tree with a completely distinct alphabet symbol, right? Then everything will be different, and you'll have this property with 1 here. But the interesting thing is that you can actually do this labeling with a really small sized alphabet. So what Schulman shows is that you only need an alphabet of size that's d to the power something that depends on epsilon to achieve such a labeling. So the crucial thing here is the size of this alphabet does not depend on the number of vertices in the tree. It only depends on d and epsilon. Okay, and it's not trivial to construct such a tree code. For example, it's easy to see that just a completely random labeling will not work. Nevertheless, Schulman shows that he shows a different way to sample the labels in such a way that you get such a tree code with good probability. Okay. So I'm not going to show you how to sample a tree code or how to construct such a thing. It is a major open problem to actually give an explicit construction of such a labeling. Okay? And that's what I'll discuss maybe at the end of the talk. But for now, let's assume that we have a tree code. So we have a labeling of the tree with these properties and see how to use it to solve the problem we care about. So let me just say, so here are some nice properties of tree codes once you have them. So imagine that the first party wants to send u as his message. So he wants to send the name of the vertex u as his message. So how can you do that? The first party can then just send the labels on the path that lead up to u in the tree code. So the first party sends that. And then what you can tell is that so the second party might receive something that's not exactly what the first party sent. They might have errors. But what you do know is that if the second party decoded v instead of u, by just finding the vertex at that depth that has the most agreement with the messages that he saw, then it must be the case that the number of errors in this interval here must be very large. Okay. It must be that the fraction of errors in this part where u and v disagree must be at least 1 minus epsilon over 2 times the length of that part. So that's the crucial feature we'll use. If the second party decoded v instead of u, then you know something about the part where u and v disagree. the suffix where u and v disagree, there have to be lots of errors in just that part. Is that clear to everyone? Maybe you want to ask a question? It would help.
Why over 2? That I understand. Why?
Because I'm counting the number of errors. The distance in this part is 1 minus epsilon times the length here. But with 50% errors, you could interpolate between two strings, right? So
Decoding is mostly likely with decoding.
yes. So what I'm every time the way I'm going to do decoding is, the first party sends this path, and the second party will find the vertex v that's closest to this path in Hamming distance, right? Whose labels are the closest in Hamming distance, and that's going to be the decoding algorithm. Okay, so the point is that if the fraction of errors here, the first party sent u here, if the fraction of errors was smaller than this number, then u would definitely be closer than v. Okay, because u and v agree on all the labels in this part, so they're kind of doing exactly the same, and the only place where they're doing differently is in this part of the string. So if the fraction of errors there is smaller, then u would be more likely than v. Okay, so that's the key property that we'll use. Another thing I want to point out is that tree codes imply the existence of classical error correcting codes. Okay, so I want to say that if you have a tree code, then you also have a classical error correcting code, and that's for example given just by this construction. Suppose you want to encode some string x that's of length n, then here's how you can encode it. What you can send is send the symbols that correspond to the path that's given by x concatenated with a bunch of ones. So say you have x here and n ones. Okay, so you want to send x, you send all the symbols up to x and then send all of these symbols too. And then this forms a good error correcting code because, if x and y are not the same, then the tree code property means that if you look at the labels of x with all these ones and the labels of y with all these ones, then it must be that you have a very large Hamming distance in this part of the string. So the code words that correspond to the labels of these paths will be very far apart in Hamming distance. Okay. But they're sort of stronger than normal codes. And another nice thing about them versus normal codes is, usually in error correcting code, if you have a message X and you want to send it, you have to see the entire message and then encode the entire message into a code word, right? Using tree codes, you can sort of start transmitting right away. So you get the first symbol of X, you send a label. You get the second symbol of X, you send another label. And if there are no errors, then after n steps, the receiver already knows what you were sending. If there are errors, the receiver needs to wait a little more to decode. Okay, so it's sort of a really faster way of encoding messages than using an error correcting code. Okay. So those are tree codes. Now let's try and use them to solve the problem we care about. So again, this is the problem. And the way we're going to solve this problem is we're going to essentially run the trivial protocol we talked about, except we'll use tree codes to encode and decode the messages that are being transmitted. Okay. So just a reminder of what the trivial protocol was. We just like to announce in every step the edge that extends the path that we know about. So here's how we'll use tree codes. So both parties will ahead of time know some construction of a tree code, and that's what's drawn here. And the vertices in this tree code will be interpreted as subsets of the edges of this input tree. Okay, in the following way. The vertex that's the root that's at the root of the tree code corresponds to the empty set of edges. Okay. All the vertices that at the next level of the tree code corresponds to edges of size at most 1 in this set of edges. Okay. So in general, every vertex at depth k in the tree code is going to correspond to a set of edges in this picture which has at most k edges in it. So I'll give you an example and then maybe it'll be a little more clear. So suppose you initially, in your protocol, the parties were sending messages like this. So those were the edges of the tree, and the first party was sending 1, then the second party was responding with edge number 4, and then the first party was responding again with edge number 9. Then now in the new protocol that uses tree codes, the parties will do this instead. They know this tree code, which corresponds, all the vertices correspond to sets of edges. And the first party wants to send a 1. Okay? So that corresponds to saying that his set of edges is going to change from the empty set to announcing a 1. So he'll send the symbol A, which is the symbol labeling the edge that goes from the empty set to the set containing 1. Okay. So he'll send A. Now the second party wants to announce 4, but she doesn't just send 4 in the clear. Instead, she looks at the tree code and she says, okay, so she wants to make her set of edges that she's announced so far be 4. So she'll send the symbol B. Yeah.
So what's the additive? I mean, what's the degree of the tree code you're going to use?
It's 2 to the n so far, right now.
Okay, so I see. So n is the depth of the protocol, and the protocol itself is binary, but the tree code is 2 to the n.
Yeah. 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 So as I said, for now I'm just going to assume, that for free I'm going to use this huge alphabet, and later I'll show you that actually everything will work even with the binary messages, but that'll be more complicated. So for now, let's just understand this.
But I'm not asking. I mean, I'm asking about the degree in the tree code, right? Not a priori on the alphabet. Of course, it's.
Those will both be the same. So eventually, what will happen is both the tree code will become binary and the alphabet will become small. Okay. So for now, the tree code has degree that's exponential in n, and the alphabet symbols are huge. But eventually, this problem will go away. More questions? Okay, so one thing to keep in mind here is that what's going on is each party is sort of using this tree code independently, in the sense that, so in the first step, the party sends A to say that he's announced 1, and then in the third step here, the party announces 9. So to do that, he just wants to change the set of edges that he's announced from 1 to 1, 9. So he just sends the symbol F. Which corresponds to saying that now he's adding the edge 9 to the set of edges that he's announced.
Is it important that they use the same tree code?
No, it's not. But they need to know what each other is using.
1,9 is there because this is consistent with something, right? I mean, there is no 117.
As I've defined it so far, actually that's exactly how we'll save the alphabet size. But as I've defined it so far, every set of size 2 is here. Okay? Eventually, we'll reduce alphabet size by saying that not every set is possible. Okay, so each party is kind of using the tree code independently to encode their messages. And they're basically trying to encode the set of edges that they've announced so far. That's how we want to think about this. So here's how the protocol runs now. So I'm going to describe the protocol from the perspective of the first party. Okay? So from the perspective of the first party, he's going to keep track of 2 things. So he knows so far the edges that he's announced, and these he really knows, right? The adversary cannot corrupt his memory. So he knows the edges he's announced. But he doesn't know exactly what edges were announced by the second party. So instead, he uses a proxy, which is this B prime that I've drawn there, he keeps track of kind of what is his best guess for the vertex in this tree that corresponds to the second party's messages. And this decodes to some subset of edges. Okay. So when the protocol starts, the first party, so initially A and B prime are both empty. Right? And then the first party announces this edge. And maybe the second party sends some message, which the first party probably received incorrectly. But the first party just decodes that message to find the vertex that's the most likely vertex in this layer of the tree code, which tells them some subset of edges. In this case, it's the empty set of edges. Okay. Then the first party looks at A and B prime and tries to extend the path, right? So A and B prime contains so far only this one edge, which means the first party does not know how to extend the path. So he kind of sends the symbol null. Okay, in the clear would be the symbol null. Basically, he wants to move to the set in the next level that corresponds exactly to the set of edges that he's at already. He doesn't have any new edge to add. But he still sends something in the tree code. Okay. And then the second party responds with something, which now the first party maybe decodes to this set of edges. Okay. It might decode to something that's completely inconsistent with what he knew before. But that's fine, he just continues greedily. So now he sees some other edge on that side, he just ignores it. But he does see two edges here, which he can extend. So he announces this edge. Okay. And then the second party responds with something which might again radically change the set of red edges from the first party's perspective. So now the first party will announce this edge, and so on. So maybe now the edge is changed to this, and then this. Now the first party has something to say, so he announces this edge. And the second party says something else, maybe changes it to this. Now the first party announces this edge. So kind of in every step, the first party knows exactly what he has announced, and he has some guess for what the second party announced, which might be shifting around a lot. But he just tries to reveal information that helps them proceed in every step.
When you say he announces this edge, you mean an extension, all the edges that he sent earlier to, together with that edge? Or
No.
a singleton set?
No, just the set he's at right now, he's keeping track of his location in the tree code, which corresponds to some set of edges. He's just going to add a new edge to that set, which will correspond to some child of that vertex, and send the label of the tree code label. So in every step, he's kind of just taking one step here that corresponds to adding one edge to the. Okay, so that's how the protocol goes, and it just goes for some amount of time, and hopefully, eventually, what's going to happen is the picture will look something like this. That from the first party's perspective, he'll have announced the true red-blue path in the tree. That's what we want to prove. Okay. So the protocol is pretty simple, and we just need to now make sure that it actually works.
So I'm not 100% clear. The red player, he sees the latest transmission from the blue player, and then he forgets everything he saw before and just...
No. So the red player sees the latest transmission. He knows all the transmissions of the blue players. He decodes this entire string to a vertex in the tree code. Okay, so that's why the blue, from the blue player's perspective, the red edges might change quite a bit, because after receiving one more symbol here, it might change something in the path, in the past by a lot. So like,
Because it's most likely with decoding, so like by changing one
Right,
symbol,
right,
then
yeah. Okay. Any other questions? Yeah.
If that's the case, how come the new decoded message is always a child of the blue? Why doesn't the blue guy, why can you proceed always?
Oh, the blue guy is not doing any, this is the perspective of the first party, okay? So from the perspective of the first party, he knows A exactly. He's doing the decoding only on B, to decode B prime. From the perspective of the second party, the blue edges are shifting all over the place. The second party knows B exactly. and is just doing the decoding to decode A. Okay, so this view that I've drawn here is only the first party's view.
So some red messages, the way the blue player sees it, make no sense, right?
Yeah, that's right.
And those he ignores. Or he tries to...
No, as I described, he just dumbly continues.
Those he tries to reinterpret by allowing more errors? Or?
No, he just reinterprets. Everything decodes to some vertex in the tree code, which corresponds to some set. So he puts that set on. It might be a crazy set here that doesn't make any sense, but the protocol still makes sense. Yeah.
I think one thing that might clarify is that at each step, the blue player looks at what the red player has said. Now, he had some interpretation of what that meant in the previous round. He forgets that interpretation, but he remembers...
He remembers all the transmissions.
He decodes the whole sequence of transmissions.
That's right. Yeah, so the actual decoding from the previous step is completely forgotten. He just looks at the transmissions and redecodes them into the tree code.
It's like history. You rewrite history after each war.
If I was more of a poet, maybe I would have. Okay, so is everybody clear with the protocol? All right, so now, the hard part is to figure out why does this actually work, right? Because it seems crazy. So in order to analyze this, so let me introduce some notation. So in each round of the protocol, there are kind of 4 sets that are in play, 4 sets of edges. There's the sets A and B, which are the true sets of edges that have been announced so far by each party. And then there are the decodings A prime and B prime. Right? The second party decodes A prime from the transmissions, and the first party decodes B prime. And these might be really far from A and B. So one thing that's really useful to keep in mind, one parameter that's really useful is this parameter T of K, which is the time at which the first K edges on the correct path have been announced. Okay, they have been included in A and B. Okay. So let me just draw a picture so it's clear. So now this is a different picture from what I had before. Now these are the true sets A and B, not the decoded sets. Okay, so as the protocol runs, in the first step, surely the first party will announce the first edge. So the first step already is T1. Then maybe this is what happens in the second step. They both announced some crazy edges because of the errors. And at this point, the second party announced the second edge in the correct path. Okay, so that's T2. That's the point I'll call T2. Okay, so at this point, one of the parties has announced the third edge in the correct path. But this is not yet T3 because one of the parties announced the fourth edge. But when all of the first 4 edges have been announced, that's when T4 happens. Okay, so in general, TK is the time when all of the first K edges have been announced by both parties.
But essentially, how?
So that's just a number that's interesting. So if you want to argue that the protocol is correct, it better be the case that Tn happens before the protocol ends, right? So that's definitely one thing we need to ensure. But that itself does not guarantee that the parties know that this happened. Okay, so that's not enough. But that's definitely necessary. So let's just try and think about that. So the intuition is basically what we're going to try and show is that if there's a large gap between Tk and Tk plus 1, so if at this point all the first K edges have been announced, but then for a long time the next edge is not announced, then there must be a large number of errors in this interval. Okay, that's what we're going to try and argue.
Sorry, can you repeat what this announcing an edge means? Confused.
Okay, announcing an edge means, so as the parties continue, the first party is maintaining the set A, which is the set of edges that he's announced. Right? In every step, the parties adding an edge, potentially adding an edge to the set A, and then decoding B prime, which is this guess for the set of edges that have been announced by the second party. That's what I mean. Is that clear?
Of course, but then what does it mean to say k edges have been announced? Because every round there is an edge being always transmitted, right?
No, not just k edges being announced, but k edges on this correct path. So there's this correct red-blue path, and I'm interested in how many of those edges have been announced. So at this point, for example, only one edge has been announced from the correct path. This is B prime, but the first party announced this edge, and that edge is not on the correct path. Okay, so I'm not counting that. So when I say tk, I mean the time at which the first k edges on the correct path are included in A union B.
But that doesn't mean the other party actually got it correctly.
That's right. That's right. Yeah, so it just means that someone has said it. Okay. Okay, so this is what I'm going to try and argue is that there can, if there can be big gaps between tk and tk plus 1, it might have been that everybody, that the first k edges have been announced, but still we have to wait a long time for the k plus first edge to be announced. But this only happens if the adversary inserts a lot of errors into this part of the communication. Okay. So in order to understand how that can happen, let's define a second quantity. So the quantity is MR, and this is the time up to which the decodings are consistent in time in round R. So what do I mean? So say we're at round R, and these are the 4 sets that are relevant to this round. So A and B are the sets of edges that have been announced so far, and A prime and B prime are the decodings of the parties that correspond to these sets. So in general, A prime and B prime will not be equal to A and B, right? But they will be equal up to some point. So like B prime and B are 2 vertices in the tree code, and there's some least common ancestor that B prime and B have. So MR is the sort of the maximum of the 2 least common ancestors. Okay, so in round R, MR is like before MR, the decodings are consistent. That's what it means. So if you look before MR, B and B prime are the same. The decoding is correct. And before MR, A and A prime are the same. The errors only happen after MR. The errors in the decoding only happen after MR.
So this can go up and down, right?
This can go up and down, yeah. So it's not monotone at all. It might be that in R plus 1, MR goes farther back or even forward. Okay. So here's how we'll prove that the protocol succeeds. So what's written here proves that the protocol succeeds after n over epsilon rounds. Okay. So let me say what it means. So it says that if the error rate is small enough, then after n over epsilon rounds, if you look at m of the last round, we'll prove that that's at least t of n. Which means that t of n will occur, if this is the last round, t of n will occur somewhere here. In other words, both parties will have decoded the first, the entire, all the n edges of the correct path correctly. And that means they both know what the outcome of the protocol is. Because no other edges can change their belief about what happened in the real protocol once they know the all n edges of the correct path.
So there are 2 epsilons here, right? For the tree code and for the communication.
It's the same epsilon. So we'll use a tree code with distance 1 minus epsilon, and the error rate for the communication will be 1/4 minus epsilon.
So since we said before that the M of R can so the question is, do they know that they know?
We'll prove this no matter what happens in the protocol. At this round, this will be true.
No, but
so they know.
So this is something I'm still not sure about. So do they know that they know? So the moment they both have a path that's consistent and is true, But what's the proof that they've accomplished their goal? Do they know this?
Yeah, they do, because what they will do, so here's what the parties are going to do. They will run for this many rounds, and at the last, when the first party terminates, he has a set A and B prime. And together these give some edges in the tree, and the proof will guarantee that there will be a unique path that hits one leaf in this, and that's the leaf he's going to output.
The application proves to them that they're right. It's the theorem that proves to them that they're right.
Yeah. The theorem proves that they'll always have just this one path which indicates what the simulation is.
So in principle, B prime could have two inconsistent edges, right? So he would have like two passes already.
I'm confused.
So B prime can be a set of inconsistent edges, including two red edges starting from the same vertex.
Good. Actually, so we'll forbid any such inconsistencies in the tree code. That's easy to do. So we'll always make sure that the edges, the vertices in the tree code only correspond to edges that don't, come from the same place. Okay, good. Yeah, that's a good point. So eventually, yeah. So every vertex here is going to correspond to some subset of edges that could possibly be a subset of the inputs to the second party. Okay, so this is what we're going to prove. Well, I'm sort of running out of time, but I think it's good. We'll spend more time here and less on the rest of what I plan to talk about. So that's our goal now, to prove that. So here's the first lemma that's useful for this. And this lemma just follows from the property of tree codes. Okay, so lemma says that the fraction of errors in any round R, the fraction of errors in the interval mr plus 1 to r must be at least 1 minus epsilon over 4. Okay, and this just follows from the tree code property, because if you look at the interval r to mr plus 1, that corresponds to exactly, this kind of part in the tree code. And the tree code property we talked about before says that this means that the second player's transmissions must have experienced an error rate of 1 minus epsilon over 2. Okay. So the second player experiences 1 minus epsilon over 2 fraction of errors. That means overall they're experiencing 1 minus epsilon over 4 fraction of errors. Okay. Good, so that's one lemma. The second lemma says that if r plus 1 is less than tk, then it must be the case that mr is less than tk minus 1. In other words, sort of the r's and the mr's pairs interleave with the tk minus 1 pairs. Okay, and maybe it'll be clear when you see the proof. It's a simple proof. Suppose it doesn't happen. Suppose the picture looks more like this. There's a round r and mr that are between tk minus 1 and tk. Then this contradicts the behavior of the protocol, because at round r, if mr is after tk minus 1, that means both parties know the first k minus 1 edges correctly. So that means one of them will announce immediately the kth edge. Okay. So if this happens, then tk must follow right after round r. And that's exactly what the lemma says. So it says that if r is sort of much before tk, then mr must be before tk minus 1.
So in your one round, most people speak.
In each round, both people speak. Yeah.
So question, so tk is when the kth edge is announced, right? But the other person may not hear that edge.
That's true. But because mr is after tk minus 1, that means that both parties have decoded up to the first k minus 1 edges correctly. Okay. So the k minus first edge is announced here, but at some point later, it's only now that is it clear what I'm saying?
So, I mean, maybe I'm confused about what TK... Does TK mean that both of us have to agree on the first K prefix?
No, it just means both of us have announced them, have tried to transmit the first K edges.
Between the two of us.
It doesn't mean that we've decoded them correctly.
Right. So the
It just means they've been announced.
set A union B contains the K.
Yeah, exactly. The set A union B contains it, and in this proof we're using the fact that because MR is after TK minus 1, even the sets A prime and B prime contain the first K minus 1 edges. Okay, so with these two lemmas now, we're basically down to the proof. So we want to prove that in the last round, the M of the last round is at least T of n. So that's what we argued would be enough to argue that the protocol is correct. Suppose that doesn't happen, then the picture should sort of look like this, right? If M of the last round is less than T of n, then applying lemma 2, we get that sort of M of if the I'll explain the intuition. I think there's some off by one application in this slide. But the intuition is if you look at R and MR, then they must sort of go past T of n minus 1. And then by the first lemma, we know that there's a higher error rate in this region. And then we can apply the same argument to this new R. So set R to be this new M of this number. And that number is now less than Tn minus 1, which means by lemma 2, M of this number must be before Tn minus 2. So in this way, we can kind of cover. You cannot do this forever. Eventually, you'll end up because you run out of T's. Okay, so you cover the entire transcript here with these error regions. And that's the idea of the proof. So basically what you find is you find sort of between these R and MRs, there's a lot of errors. And in the proof what happens is there's a little bit of, there are these indices which are off by 1. So there are little intervals here with 1 or 2 rounds where there are no errors. Okay? But for most of the protocol, for most of the time interval, you can find intervals with lots of errors. And that will show that. So if this didn't happen, then overall there must be lots of errors throughout the protocol.
Why you need that to run n over epsilon rounds? Because you need that your original protocol take only epsilon fraction.
Exactly. Yeah. So exactly. So you need the blow up in the communication to be large enough so that these black parts are not a large fraction of the entire communication. So that's the basic idea. And now, as Nati said, so this proves the theorem that if you use this huge alphabet, then you can solve the problem, even if there are 1 minus epsilon over 4 errors. And now you can reduce the alphabet size by realizing that actually you don't need to encode all possible sets of edges here, but only those edges that could show up. And you can reduce the size of the number of sets that show up is actually much smaller. So one thing is what you said, that you cannot have 2 red edges from the same place. That's one thing that cannot happen. But another observation you can make is that if this is a set of edges that have been announced so far, like in every step, each party will announce only an edge that's close to some edge of the edge that he announced before, right? Like from A's perspective, no matter what set of edges B prime that he sees, he might announce this edge or this edge, or this edge or this edge. There's no way he'll announce some edge that's here, because he'll never find a path within his set of edges that gets close enough to that edge. So this reduces the space of edges by a lot, because the total number of edges A has announced so far is only polynomial. Okay? So that reduces the alphabet size to something that's polynomial, in n. And then finally, you can actually reduce the alphabet to just be bits by doing sort of the most naive thing you could imagine. Instead of sending edges, we'll encode the names of those edges in binary and transmit them bit by bit using a tree code. Okay, so that's the protocol. So in every step, kind of a player might be in the middle of transmitting the name of an edge, or might have been done. If he's in the middle, he continues transmitting. Okay.
Your alphabet is still not binary because you have a tree code over it.
Oh, that's right. That's right. Good. Yeah. So So we'll encode using a binary, but then the tree code is still using constant size alphabet. Right. Eventually, you can even get it down to binary by using a tree code that has binary strings as the labels. Okay. But for a constant size alphabet, you just announce sort of the bits of the names of the edges. And then you might, at first you might think that this might cause a log factor blow up in the communication because, each message might be log n bits. But it turns out that can be avoided, okay? So it turns out that the messages we're sending can always be encoded in such a way that you're kind of sending, each edge that you're sending is like, you need to say, this is an edge that's a neighbor of this other edge that I announced before. So you send in binary the offset from the last edge you announced, and you continue in this way. And then you can show using a convexity argument that the total contribution of the bits is actually not too much. It's only a constant factor. Yeah.
Is this a variable length code then that's being used so when I announce the next edge in binary, is the binary string of different length or is it always the same length?
No, it's of different length.
So sometimes the edge I'll choose, I'll have to state more things in binary.
Yeah, that's right.
So moving to variable length code is what lets this happen.
I don't know what variable length code means, but in every step you announce you're announcing you want to send a string which might be of different length from the string you were sending before. But you'll use a tree code, the same tree code that we talked about, to encode each part of that string.
Do I know in advance how long this string will be for at that stage?
No.
I mean, basically just, you want to say go X steps back and go to the right child.
Yeah.
And you want to encode this in log X plus constant number of bits.
Shouldn't we use usual error correction codes above the tree code to preserve the error rate when we go to binary from the huge alphabet?
That's one you can do that, but it turns out you can just build a tree code that has the binary strings on it, which basically is doing that in some sense. Okay, more questions? Okay, so that's pretty much all I was going to say about encoding protocols. So it turns out you can tolerate an error rate of 1 minus epsilon over 4 if you use an alphabet size of constant. And if you want to use a binary alphabet, you can tolerate an error rate of 1 minus epsilon over 8. And there's sort of some good reason why it's hard to go past the error rate of 1 over 4. Although Bernard will talk about one way to go past this error rate. And that's because, if the model for communication is that in every step the players agree about who is going to speak in that step, then intuitively, in any protocol, in any simulation that you construct, one of the parties will be speaking half the time. And the adversary can always focus all of their errors on that party. And with a 50% error rate on that party, they can corrupt any such protocol. Okay, so 1 over 4 is sort of the natural point at which you should not be able to recover. For binary, we don't know if 1 over 8 is the right number, but okay. So, any questions about this before I move on? So I've gone much longer than I intended to. I was going to tell you 2 applications and a candidate construction of tree codes. But maybe I'll skip this first application. I'll just tell you roughly what it is. So I talked about how tree codes can be used to encode circuits with errors in this way if you have two circuits that are talking to each other. But here's maybe a little more surprising model for errors that tree codes can also be used to solve. Suppose you have a circuit and the circuits now. So the reason we got to this is we were thinking about, what kind of adversarial errors can you tolerate in circuits? Which at first you think, nothing, because if there's a corruption at the output gate, the whole circuit is ruined, right? But if you think about what corruptions can be tolerated and what can't, you notice something interesting. Obviously, if you replace the output gate with a constant, then the circuit is ruined. If you negate the output gate, then the entire circuit is ruined. But what if you flip an AND gate for an OR gate? Okay, then it's not clear. It's not clear. One such error may not ruin the circuit, right? Like in this circuit, the computation is still fine because there was 1, 1 here. It doesn't matter if it's an AND or an OR. Okay, and actually what we proved is that these kinds of errors you can actually tolerate quite well. So what we showed using tree codes is that you can always take any circuit of depth d and encode it to get a new circuit of depth order d, such that the new circuit computes exactly the same thing as the old circuit, as long as at most, say 10% of every input-output path is corrupted with these AND OR switches. Okay. So the adversary is allowed to take on any input-output path and corrupt up to 10% of the gates there by flipping ANDs to ORs or ORs to ANDs. And the circuit, the resilient circuit will still work.
And what about the size?
There's no control on size. Yeah. So that's actually a really interesting open question, is to do the same thing but bounding the size instead of the depth. Okay. So I'll skip. I think it's a beautiful question. It's also connected to codes in a different way, but I'll skip it. So I'll just try to quickly tell you another application. And this is to the problem of constructing metric embeddings. So the problem here is, specifically it shows up when you want to try and embed trees into L1. So what does that mean? So here's a tree. And what we would like to do is map all the vertices of the tree to points in Euclidean space in such a way that the distances, the L1 distances in the Euclidean space correspond to the distances on the tree. Okay. So for example, here's one way to do this mapping for this tree. So I've mapped each of these vertices to these points in Euclidean space. And you can see that the L1 distance between these two vertices is 1. And that's the same. In the tree it's 1, and in the Euclidean space, in L1 it's also 1. Okay, and the same way, the distance from this to this is 2, and it's the same in the tree. So we'd like to be able to do that for every tree. That's the question. And the thing we're trying to optimize is we're trying to minimize the number of dimensions you need to use in the Euclidean space in order to achieve this. So, one thing that's easy to do is you can always embed the line using one dimension, right? So that's one special case that's easy to handle. And then perhaps the next example that you would think of is how do you encode the complete binary tree, right? That's the other extreme. It completely branches. So let's talk about that, and this is exactly where you can use tree codes. So I'd like to encode this into L1, but I'd like to have a very small dimension. So let's do it by first let's put a labeling on the edges of this tree that correspond to a tree code. Okay? So we know that you can label it using a constant size alphabet if you want constant relative distance. And then here's the idea. Here's how you do the embedding. You put the root of the tree at the origin. Okay. The number of dimensions here is going to be log n if there are n vertices in this picture. And then this vertex will be mapped to the point E2 followed by zeros, where E2 is a unit vector in k-dimensional space in direction 2. Okay? So each one of these coordinates is a k-dimensional vector, and they're going to be log n such coordinates. So this coordinate goes to E2, 0, 0, 0. This one will go to E2, E3, 0, 0, 0. Okay? So you basically use the labels of the tree code to figure out where to embed things just by concatenating the labels using basis vectors. Okay, so now you see, so what is the distance between these two? It should be 2, and it is, right? So these two already share E2 in the first coordinate, and they disagree on, this one has E1 here and E3 here. So the L1 distance between these two vectors is 2, which is exactly the tree code, which is exactly the distance in the tree, right? 1, 2. So in general, it turns out that the tree code property is exactly what you want to make sure that this embedding preserves the distances at least up to some error. Okay, so this construction is used to show that you can embed any tree using order log n dimension.
So you're trying to guarantee distortion at most 1 plus epsilon, right?
Yes. Yeah. So the distance of the tree code will the fact that sometimes the labels are equal will give an error in the relationship between the distance in the L1 and distance versus distance in the graphs. This error is necessary, I can show. But this idea was actually used to then by Lee, Mesme, and Maharami to show how to handle. Oh, I wrote all graphs, but I meant trees. You can actually handle all trees in log n dimensions. Okay, so it's another reason why if you could construct explicit tree codes that would, translate to giving explicit embeddings. So it's another motivation to study this thing.
Is this the only way known to achieve this embedding?
Before this construction, there was something that did log squared n dimensions, and that uses different ideas. But with log n dimensions, this is the only way as far as I know.
Trees.
For trees, yeah. Everything is for trees.
But you are correct.
No, I made a mistake. That's what I said. Yeah. This actually should be trees. This is all trees.
So what's the difference between the two lines?
What? Oh, this is a binary tree. And arbitrary trees can be paths. So what happens to arbitrary tree? You have to mix the two ideas that I talked about. Sometimes you have a path, and then you don't want to add more dimensions. And sometimes you have something that fans out a lot. And so the final construction sort of mixes these two ideas. In a way, it's complicated to get show that for all trees you can embed it into log n dimensions.
What's the best known for all graphs?
Not sure. It's something like n to the power 1 over. I think it's polynomial in.
The diamond graph.
The diamond,
Recursive diamond graph.
So it's polynomial in n. Is that right?
Because it follows from lower bounds for dimension reduction in L1.
It's like those below the canopy.
Okay, so that's at least one thing. Maybe I'll just stop by after I show you this candidate construction of tree codes, which was recently suggested by Moore and Schulman. So this is a construction that they believe to be true. I think they even use computers to check that for some depth it is a tree code. But there's a conjecture on there's a conjecture about some exponential sum that, if true, would imply that this is a tree code. So what is the construction? So the basic idea is every vertex of the tree will be associated with some point, some complex number of unit magnitude. Okay, so some point in the circle. And then the actual labels will be given by seeing sort of which quadrant that point is in. Okay, so the label of this is 2 because I is in the second quadrant. Okay, the label of this is 4 because Z is in the fourth quadrant. Okay, so how are these complex numbers picked? They're picked recursively by solving this equation. So the root is labeled 1. And then the next two guys are the two square roots of 1 cubed, which are +1 and -1. And then the two children of -1 are the two square roots of -1, which is -1 cubed. Okay, and so on. So what happens is, at the second level, you get both the second roots of unity. At the next level, you get all the fourth roots of unity, and so on. But they're permuted in some way. So, if you like number theory, then that's something you can think about. All right, so I'll stop there. I'll just say, so for me, the most interesting question that's related to all the problems I talked about here is, can you construct tree codes explicitly? Can you find an algorithm that actually constructs a tree code? Thanks. Yeah.
Regarding the construction of tree codes, there's no efficient algorithm. Like the sampling is not efficient.
I mean, the sampling works with 99% probability, but there's no way to certify that what you got is correct.
But it's practical.
The way how Schulman constructed something will not be 99% correct.
No, it will be.
No.
I mean, his convolution construction, if you use, large, as you increase the field size, the probability of success will be higher and higher.
In this context, a bigger problem is not just, even if I could write down a tree code, how do I decode it? Right? If the tree code has like pseudo-random structure, and I want to find the path that's like closest to a given string, good luck doing that, right? Even if I can compute every label on the path very efficiently, decoding would still be.
We're at the same point when they first constructed random codes. You need to come up with ideas to build these things and decode them.